What's up, everybody? Welcome to the weekly live stream on SAT Khan Academy problems. And today we are working on solving quadratic and exponential word problems, level 2. I'm just doing a quick sound check and make sure we are good to go here. And we are. All right. Without further ado, let us begin. Here we go. So as always, I'm doing these problems for the first time. If you find this stuff helpful, useful, and you want more from Scalar Learning, make sure to subscribe. Like the video if you like it, but definitely subscribe so you can keep up to date on all our new stuff. We got a new math music video coming out in the next week, which should be really exciting, on systems of equations, and that is all being integrated into our Power 800 SAT Math video course, which you should definitely check out if you haven't done so yet. You can click in the link below for more details and a 50% discount. All right, without further ado, let us start quadratic and exponential word problems. Let's begin. And as always, I'm solving these for the first time, so doing it with you. It's part of the fun. The amount of carbon-14 in a sample decreases once the organism from which it came is no longer alive. A sample of an ancient fern fossil contains 42% of the amount of carbon in living ferns. The fraction of carbon-14 F left in the fossil sample T years after it died can be modeled by the following function. F of T equals 2 to the negative T, and this is a calculator problem, negative T 5730, like this. Approximately how old is this fossil? Well, it's saying the fraction is this guy, is over here, which we can represent that percentage as a fraction as this. Maybe divide the top and bottom by 2, and we get 21 over 50. I don't think that can be reduced anymore. And now we need to solve for T. All right. Personally, I would do logarithms of this. So I would take log of both sides, since we can use a calculator. And this allows us to bring down this exponent over here. So it becomes log of 21 over 50 equals, this is just basic logarithm rules. We can bring down the exponent like this, times log of 2. This is log base 10, by the way. We could do log base anything. I'm just doing log base 10 because that's what's on a calculator. And we can divide both sides by log 2. And then finally, we'd have to multiply by negative 57 over 30. But before we do that, let's at least calculate what this value is. It says approximately, right? So we do log of 21 over 50. I'm just going to say log of 0.42. So log of 0.42 divided by log of 2. Log of 2 equals negative 1.252. Negative 1.252, I rounded to the nearest thousandth, equals T over, I'm just moving this negative to the 5730 just to be easier because I'm going to shoot that all over together. Then we multiply the left side by this value to isolate T. So we take our answer, multiply by negative 5730 times 5. So I'll just multiply it by positive 5730, and I know our answer is negative. So it's about negative 71 years. I mean, so positive 71 years. That's the approximate age. All right, let's see if there's an answer close to this. And I guess 7,000 is the closest. So I believe this is correct. Let's make sure we are good to go. And we are good to go. Here's the explanation. Same thing. So they plugged in 0.42 instead of 21 over 50. I just turned it into a fraction. And that is about it. They didn't use logarithms. What did they do here? Okay, so they did it a different way. That I guess they plugged in a value. They plugged in a value to kind of figure this out. So they're like 10,000. Yeah, so they basically plugged in a value and kind of figured it backwards. I think logarithms are a better way to go if you have used them. Probably you have in Algebra 2, even pre-calc. Question number 2, no calculator, so I cannot use a calculator for this. An investment lost 5% of the balance each month for the last year. The amount of investment on January 1st of last year was 10,000. So every month they're losing 5%. Which of the following functions models the amount of the investment at the end of month n, where n is between 1 and 12? Well, let's think about this for a second. Every month they're losing, it's got to be C. But every month, so every month we know what it's going to be after the first month. So at the first month, right, we should be down 5%. 5% of 10,000 is is $500. Right, 500, because we know 500 times 20 would get us back to 10,000. 20 times 5% gets us back to 100%. So after 1 year, we're at 9,500. Now, I can tell you this value is wrong because this actually increases it to, that would be 10,500 for n equals 1. That's wrong. And this is supposed to be, I is supposed to represent, let me just make sure, models the amount of investment at the end of month n. Yeah, because it's losing money, it should be going down. So this is out. This is losing, but this is just saying we're losing 0.05 every month, which doesn't make any sense. We should be losing 500 and then a little bit less, because then it's 5% of 9,500. But so this one's totally incorrect. This one's good. This one, again, it's going to be increasing. It's not decreasing, so that's another problem. C is our only right answer. Now, the reason why it's 0.95 and not 0.05 is because after 1 year, we have 95% left of what we originally had. After 2 years, we have 95% of 95% of what we originally had. So it'd be like 0.95 times our 10,000. And then they're taking 0.95 of this again, which is why this actually makes sense. That should be right, and we are good. Question number 3. Kudzu is a vine that is introduced to the U.S. as an ornamental plant. Starting in the year 1935, kudzu was planted throughout the Southeast to combat soil erosion. By 1946, kudzu covered approximately 3 million acres. Okay. So 1935, it was planted, we'll say 0, I guess. 1946, it was gone to 3 million. 60 years later, 2006, I guess, it was at 7 million. Which of the following functions best models the amount of kudzu in millions of acres T years after 1946? So let's see, 60 years later, 7 million acres were covered. So this is, again, after 1946. We don't care. So first of all, when t equals 0, and it's in millions. So when t equals 0, this equation should equal 3, because we're talking starting at 1946. So actually, we don't care about this. For this is true. For this is true. This is definitely wrong, but we'll come back to the y later. For this is not true, this would be 4 million, because it'd be this to the 0th power plus 1, so plus 3. 1 plus 3 is, because anything to the 0th power is 1. So C is out. And D is definitely out because, well, 0.14. We don't necessarily know if it's exponential. Actually, D, I'll leave it in for now. But C is out, and also B. Well, we have to leave B in for now, but I'll show you how to eliminate B in a second. The problem with B is when t equals 1, meaning by 1947, this equation would yield 3 times 0.014. It's a no calculator problem, but I can tell you what that is. 0.014. I'll do it really quickly. It's 12, 0, 3. So it's 2, 4, and then we go 1, 2, 3. So it'd go from 3 million down to 0.042 million. That's actually obviously not the way it's going. It's just increasing. So this is out. It's either going to be A or D, and it's going to be, my assumption is going to be A. But now we have to check, we can check one other point, which is right here. So this is at where t equals 60, we should be getting 7. All right. So now let's quickly, I'll plug it into D so we can eliminate D and assume that A is correct. If we had a calculator, it'd be easier, but let's quickly multiply. So now again, 60 times this plus 3 should equal 7 for D to be correct. So let's go ahead and try it out. 60 times 0.014, so 0.24, 0.06. We add them together, 8, 1, 2, 3. So we get 3 plus 0.84, which is 3.84, and that's not correct. Now, if you actually plug this into a calculator, you will get, I assume you'll get 7, but A's got to be right. And the other thing is, this is really a linear equation. Linear equations usually don't model growth. I mean, it could, but it's just usually not how things happen, because things usually, as they grow more and more, the rate of growth increases and increases because you have more plants than reproducing and so on and so forth. So it wouldn't make sense that it's linear. All right, and A is correct. Question 4. If two people in a group of 30 have two-way radio, so let's say 2 out of 30, one connection can be made. Does that make sense? If 3 people in that same group, then 3 connections can be made. I'm just making random notes here. In fact, the number of connections that are possible, C, based on having X two-way radios in a group of 30 can be modeled by this. A nice quadratic function. Which of the following represents the number of connections that can be made if 6 people in this group have two-way radios? And again, X is the number of radios. Well, we need to figure out what these constants are, because C is what value we're always solving for. What is A and what is B? Well, we can solve for them like this. We know that C equals 1 when X equals 2. Plus B times 2. Okay? So 1 equals 4A plus 2B. We know that. We also know that C equals 3 when X equals 3. So it's 3 equals 9A plus 3B, right? Now we have a system of equations, 4A plus 2B, and we can solve for A and B. So let's see, I'm going to use a little substitute, or no, I'll use elimination. I'm going to multiply this top function by 2 because I'm matching up the B's. This bottom one by positive 3. So this top one becomes negative 6 equals negative 18A minus 6B. The bottom one becomes 3 equals, 12A plus 6B. Now how nice, look how nice this is. We can just add them together. These go away. This becomes negative 6A. This becomes, as we add these, negative 3. Divide by negative 6 and A equals 1/2. Okay, so that's really nice. If A equals 1/2, let's plug it in here and let's get B. This is 1 equals 1/2 of 4, which is 2, plus 2B minus 2 minus 2. 2B equals negative 1. B equals negative 1/2. So our new equation is C equals 1/2 x squared minus 1/2 x. And now we want to know, if x equals 6, what is C? Plug a 6 in there and there. So we get 1/2 times 6 squared minus 1/2 times 6. And if you wanted to, you could plug 2 in and 3 in and make sure we're getting 1 and 3. I'm going to assume for now it's correct. So we have 1/2 times 36 minus 1/2 times 6. This is 18. 1/2 of 6 is 3. So we should have 15 connections. If I did plug 3 into this equation, let's just make sure that's right, I would get 9. I would get 4.5 minus 1.5, which is 3. So I think it works. And 15 should be the correct answer. Let's see if we're right. And that is correct. Finally, question 5 of 5. Here we go. From 2004 to 2007, the number of cars produced in China can be approximated by a quadratic function. The minimum production during this time occurred in 2004, with China producing approximately 5,234.5 cars during that year. And this is a no calculator, by the way. The following year, China produced 5,707.69 thousand cars. According to the data, approximately how many cars did China produce in 2006? All right, so let's see. Say minimum production occurred in 2004. So that means we'd have like some sort of a parabola like this. Here's the minimum production in 2004. We could say this maybe is 2003. And this would be 5,000. Let's do a little thing. I'm just making this up as I go. I don't know if this is gonna get us to the answer, but this is how I'm processing it. 5234.5. The following year in 2005, China produced 57, let's say. What is it? 5707. Approximately how many cars did China produce in 2006? So 2006 is going to be, again, like somewhere over here. I can't get an exact answer. I can tell you it's got to be greater than 5,707. I can also tell you that the jump here, right, is only from here to here is about 500. So if this is a quadratic, this next jump should definitely be more than 500. It should be, it could be 800, it could be 1,000, but it should be more than 500. From this, I can presume, oh wait, no, this is less than 5. This is exactly, it's 477. Let's be precise. 473, sorry. 473. And then if we were going to go to 6181, my problem with that is this is a jump of 474. You know, see, that's the problem. It's almost the exact same jump. And if it's truly quadratic, it shouldn't be going up by that same amount at that next juncture. It should be a faster increase. So this is my reasoning why. I mean, otherwise it'd be almost identical. That's my reasoning. We never have an exponential function go like this. You know what I mean? I mean, you can kind of go like that, I suppose, and then this is in between. But that's why I'm feeling like 7127 makes more sense, because then that is like a jump of 500, right? I mean, sorry, of like around 1,000. Let me just see if there's any other way that we can tackle this problem. So we got 2004, 5,234. Then the following year they go 5707.69. Now we could, let me just play this out really quickly. Say y equals x minus 2,000. Well, let's say x minus 0, because this is the starting point. Doesn't matter. Let's just say that's our minimum. X minus 0 squared. We have some a value. Plus, what is it? 52345. 524.5. Okay, so this is our starting point, and we know that when x equals 0, that's what it equals. When x equals 1, that means our a must equal, since this is 400 and, what did I say, 70, approximately 473. So let's say about 473. Right now I've gotten my a value. So we now know that a equals 473. And then when x equals 2, that would be 2 squared, which is 4. 4 times that is 16. 16 plus 280 is, let's say, 1880. And then 1880 plus this value, 5707. I don't really think you need to do all of this. Is 7587 based on my calculation there, where I'm using 0, 1, 2 for the years. So I think this is the better estimate. I think that the other one is too low. I'm gonna go ahead and enter it. Let's see if I'm right, and let's definitely read the explanation, because I'm giving it like a decent certainty. Okay, it's right. Now let's see what they say. So now, yes, so they actually tried to, okay, so they made the function like I did here in my second attempt. And they did the same thing here. A equals 473, right? And they plugged it back in. So 2 for x, 4. Oh, I just did my math wrong. I added it. Yeah, that's right. I wasn't supposed to add it to 5. Oh, it was exactly right. I was supposed to add it to 5234, not this second number. That was the mistake. And then we should get it pretty close, because this was just the estimate I did in my head. 211 7 7114. Boom. All right. So that's close enough. Anyways, I guess those were two strategies that you could use. I mean, the second one was definitely better, where you do it more algebraically, but that was just my first instinct, was to try and figure it out graphically. So that is it for today's live stream. Like I said, if you have any questions or comments on the problems that you saw, please leave them in the comment section below. And if you like what you saw, you found it helpful, and you're taking the SAT, or you're just trying to learn math of any sort in the upcoming year, make sure to subscribe for the latest videos and updates from Scalar Learning. And again, next week, I've got a new math music video coming out on systems of linear equations, which is going to be sweet. I'm rapping once again, which is super fun. So we're just waiting for the mixed and mastered version to come back. The video shoot's going to happen, and it should be out shortly. So I hope you guys enjoy that. Thank you so much for joining, and have a great rest of your week. And if I don't see you before New Year's, Happy New Year's, and best of luck in 2018. Take it easy.